Hello, everybody. We still have some people arriving, so we'll give them a couple of minutes, then we will get started. Right, let's get started. Welcome, everybody. Hello, and thank you for joining us today for our Fundamentals of Light Fastness Testing. This is a James Heal webinar. James Heal is part of the PPT group, and our sister companies are McMesson and Aluris. We have demo laboratories in Halifax in the UK and Stirling in Virginia, which you are welcome to visit as the pandemic allows. We also have a network of partners in over 60 countries around the world who can support you closer to home. Your presenter for this session is Seth Hargraves, our Technical Marketing Executive, who's based in the UK. And I'm Sharon Smorenberg, who works in the Marketing Department. Just some housekeeping before we get started. We've muted your microphones for the presentation. So if you have any questions, you can type them into the question box and we will put them to our technical team once the webinar is finished and share the answers with you via email as soon as we have them. We are also recording this webinar and you will receive a copy of it later this week. And that's all from me for now. I'll hand over to Seth and we can get started.
That's great. Thank you very much, Sharon. Hello, everyone, and welcome. So in this webinar today, we will be covering the following topics. We have defining colour and light fastness, why we test for light fastness, the factors that can impact light fastness, such as temperature, humidity, and precipitation. We have some standards, some test methods and equipment. We have conducting a light fastness test, and some assessment and common mistakes using grayscales and blue wools. So let's get the presentation started. So today we are going to explore light fastness testing, which will also encompass weathering, specifically for textiles, using a Xenon Arc tester. This is a fundamentals level webinar, so for those of you who are new to this area of testing and interested in finding out some more basic principles and methods, this is the perfect webinar for you. So firstly, what is fastness in textiles? When we talk about fastness in textiles, we are predominantly talking about colour fastness. Now, colour fastness can be defined as the resistance of a fabric to change in any of its colour characteristics and to the transfer of its colorants to adjacent materials during end use. There are various types of mechanical and environmental influences that can impact colour fastness, and these can include washing or laundering, rubbing, so think dark denim jeans onto a white sofa perhaps, liquids as well. This is quite a broad category. Some examples include rainwater on outdoor wear, seawater on swimwear. It can also include solvents and cleaning fluids, and even perspiration and saliva as well. Colour fastness can also be affected by atmospheric gases. They can also be affected by heat. So ironing clothes is a good example of this. And of course, the focus today, light. Sunlight or daylight can impact textiles in two ways. So we have directly, which is an example would be with exposure to rainwater, which can lead to the loss of colour in outdoor wear, sportswear, tents, tarpaulins, horse blankets, pram hoods, anything that is going to be used outside. And then we have indirectly. So daylight through glass can affect household upholsteries, such as curtains, carpets and sofas, or car interiors such as seating and steering wheel covers. This is what we are testing for when we are conducting light fastness. The correct term for this type of testing is colour fastness to light, as we are testing the material's resistance to fade or change of colour through exposure to sunlight and other types of illumination. It's often referred to as light fastness testing, hence the title of today's webinar. So why do we conduct this type of testing, and why is it so important? Well, the purpose of light fastness testing is to subject your test specimens to artificial light and then to assess the impact on the colour of the material. The tests are not only concerned with the total change of the specimen and the time until failure, but also how the property changes over the duration of the exposure. So all the types of colour fastness testing gauging a material's reaction to light is probably one of the most important. The effects of light can be far more subtle and unpredictable than other textile testing. So it's here that's really accurate and reliable testing is crucial. For many industries, light fastness testing is a fundamental part of research and development, as well as quality control. Materials that perform poorly in light fastness testing indicate that a product is likely to fade when exposed to light. This may result in product returns or complaints from customers. So therefore, if manufacturers can undertake light fastness testing during research and development, this can provide warning signs before the product actually goes out to market. At a commercial level, light fastness testing gives manufacturers confidence in their products. It helps them extend ranges, enter into new markets, for example, and develop innovative materials ahead of their competitors. It also enables them to meet national, international, and also retailers' standards. In an ideal world, to replicate the real-life scenario, you would expose your samples to natural sunlight in the location that they're going to be used in. This can be highly impractical for a number of reasons, including geography, cost, and time. As for the most materials, this process can actually take months or even years. So instead, most manufacturers now use laboratory testers, which simulate natural light and accelerate the testing process. The technology which does this most successfully is a xenon arc radiation tester. So let's cover a little bit of the science behind sunlight. On the screen, you can see a diagram of the sunlight spectrum. So it is the exposure to the radiant energy in sunlight. And importantly, it is the energetic UVB and UVA with its shorter wavelengths and higher intensity levels, known as irradiance. And these have the most impact and ability to break down some of the dye stuffs, which causes the fading in some textiles. Although Although only a small percentage of the whole sunlight spectrum, about 7%, UV, B and A are considered to be the largest contributing factors to the death knell of a unstable dye. The xenon arc lamp in a light fastness tester produces a light spectrum very close to that of daylight, of sunlight. So it's not as simple as putting a material under a certain type of light and observing how it performs. Light fastness testing instruments must also be able to control environmental factors to create the relevant conditions for each test and keep them consistent throughout. These factors are temperature, humidity, and precipitation. So before we move on to the details of actually testing, let's talk through each of these factors to understand the role that they play within light fastness testing. So we'll start with temperature and heat. So heat is increased during light fastness testing, and it's kept at a constant temperature according to the regional norms being tested to. The reason this is done is because heat can change the impact of light on a textile. So some examples of how it does this are evaporation. So heat can dry out some fibers, causing them to become brittle. Heat can also melt and soften some types of synthetic fibers or coated fabrics, causing them to change shape and be more susceptible to shade and color change. Thermal aging. So if coated, heat can actually cause the sample to crack or blister, like some car interiors in full sun through a window as an example. The thermal cycling from hot in the day to cold at night can actually cause stress on a material, causing it to degrade. With each successive cycle would bring further breakdown. So this is specifically true of coated fabrics, as the protective coating gets broken down, and so the ground fabric underneath, previously protected, gets exposed directly to sunlight. And there's dimensional change as well, and this can cause the breakdown of the chemicals in the dye and can make the fabric look more or less saturated in hue due to the shrinkage or the expansion of the fabric. So these are all directly related to temperature and heat. The colour of the specimen can also affect how hot the fabric will get, as black absorbs heat and white reflects it. And this is why the thermometer in the xenon arc tester is black. It's black to absorb the maximum amount of heat to record the highest reading that a specimen will be subjected to. Humidity is the amount of water held in the atmosphere. The relative humidity is expressed as a percentage of the maximum amount of moisture that can be held in the air. You will see it recorded as a percentage with the initials R and H. It can change from region to region and day to day and even hour to hour. So temperate, dry and semi-tropical regions all have different humidity levels, and these are taken into account when testing, and the corresponding climatic condition in which the product will be used in is the parameter chosen under which to test the product. The reason this matters is because too much water can actually cause some of the dye stuffs to dissolve and leave the garment with coloured runoff, or it can move the dyes, causing different tonal patterns patches within the material. This is the only water consideration for light fastness testing, such as ISO 105 B02 and AATCC 16.3. The adjustment of the effective humidity on your light fastness tester must always be made before commencing a test on an instrument. So the final environmental factor to consider is precipitation, or otherwise known as rain, which we've seen a lot of in the UK in the past few weeks. When conducting weathering testing, the basic light fastness test sees the addition of a water spray to replicate rain conditions. This is known as colour fastness to artificial weathering, which is served by the standards ISO 105 B04 and also AATCC 169. Rain can actually wash away dyes and coatings, leaving exposed areas. And cyclical wetting and drying of a material can cause physical stress. So combining light with precipitation is an important consideration for textiles, which could be exposed to both weather conditions. Well, there are several seasonal variables that add to the light and weathering degradation of a product. The fundamental principles of weather include light, which is solar UV radiation and can be both direct and indirect. There is heat and there is water. For light fastness testing, this is just humidity. For weathering testing, this is water spray during the rain cycle and humidity during the non-rain cycle. So these three factors contribute to the degradation of a textile. So let's take a look at how you test for this process, and we're going to start with the equipment that's required for testing. So you will need a xenon arc tester, such as James Heal's TrueFade as an example, which you can see on the screen. You can find different sized xenon arc testers depending on the amount of testing that you need to conduct. With your xenon arc tester, you would expect to get specimen holders or KG1 filters, the xenon arc lamp itself, and a black standard thermometer as favoured by ISO, with the option of a black panel thermometer as favoured by AATCC. It's recommended that the instrument is kept in a climate-controlled laboratory setting. Most light fastness testers require a continuous supply of distilled water or water purified to a specific grade, complying with the ISO 3696. Grades 3, 2, and 1 are all acceptable. Failure to use purified water can actually impact the accuracy of the test, and it can also harm your instrument. You will also need blue wools and mounting cards. There are two types of blue wools. There's the European blue wool standards, which is ISO 105 B08, and American blue wools from AATCC. The popular testing standard, ISO 105 B02, allows the use for both of these wool types. It must, however, be made clear that the results from different sets of references may not be identical. So we would recommend to use either one type or the other, especially if direct comparisons are to be made. The mounting cards that you use should be free from any optical brightening agents, which the blue wools and specimens are secured onto. And small non-ferrous staples can be used for this as well. To save time, you can actually purchase pre-mounted blue wools, which is what you can see on screen that we're using to test with. As a rule of thumb, light fastness is graded on a blue wool system from 1 to 8, where 1 is very poor and 8 is actually excellent. So for general apparel, a grade of around 4 or 5 is considered acceptable, whereas For curtain or automotive fabrics, for example, a grade of 7 or 8 would usually be required as a standard. The reason for this is because they can be exposed to more constant sunlight and generally are a more expensive product, which has to be colour matched with its surrounding components. So a colour change is more noticeable here than it would be in, for say, run-of-the-mill garments. You will also need specimen masks. A variety of masks are available to ensure that comparisons may be made between the irradiated and non-irradiated sections of the specimen. Masks are specified within the actual test methods themselves. So as you can see, the masks for the two different standards bodies are very different. So you must ensure that the correct ones are being used. We're going to look at the role of these masks further into the presentation to give you a little bit more context. You'll also need grayscales, which are used for assessing colour and shade change. The scales enable you to specify a rating from 1 to 5, with 5 being good and 1 being poor. Only the shade change scales are used for light fastness testing. These are the scales which have 2 different shades of grey on each side of the tile. There is no white on these scales, so if you have these, you are using the wrong ones, because they are for staining assessment, such as for washing and rubbing fastness testing. So it's the grey one in the middle that you can see on the screen that we need. Manual grading takes place using an assessment cabinet known as a light box under artificial daylight using D65 lighting. You should use a grading mask for the assessment, as this helps focus the eye to make better judgment of the results. Alternatively, you can actually use a spectrophotometer, so those can be used for this step as well. So who does the testing? Well, until recently, most manufacturers wanting to run light fastness tests on their materials had to send everything out to specialist laboratories. It's been a complex and expensive process, something definitely best left to the experts. However, technological advances have actually led to the development of modern and affordable testing equipment, which is much easier to use. So it's viable for companies in a range of industries to do the testing themselves. The one thing you will need is a technician that is trained in colour grading, especially if the assessment is being conducted by eye using the grayscales and an assessment cabinet. They'll need to be tested for colour blindness and acuity. A Farnsworth-Munsell 100 hue test is a commonly used test for this. So now that's all the equipment and what you will need for the light fastness testing in the laboratory conditions. So let's take a look at the standards and test methods in this area of testing. You can see on screen the most common standards for colour fastness to light and weathering from ISO and AATCC. We also know that retailers have developed their own test methods, many of which are loosely based on parts of the standards on this slide. AATCC 169 and ISO 105B04 are the weathering standards on this page. We've touched on this method of testing when discussing the precipitation earlier in the presentation. So as we only have limited time today, and this is only a fundamentals webinar, we'll be taking a look at commonly used standards as a good example, which is ISO 105B02. This will hopefully give you an idea of the considerations and steps required for light fastness testing. So this standard has 5 test methods, which you can see on the screen, and 3 climatic conditions. And these are A1, which is a temperate zone with normal humidity, There's A2, which is a dry zone with extremely low humidity, and A3, which you can probably guess, it's a semi-tropical and extremely high humidity. A good light fastness tester will set preloaded parameters for you, so you can be certain that you're running the test to the standard. You would select the standard that you are testing to, the method you are using, and the climatic conditions. In the case of the ISO standard, for the test to run. Each of the 5 methods produce different amounts of information. The user should select the most appropriate method for their application, along with the appropriate test climate. These are ultimately dictated by the end use of the product under testing, and they should be predetermined according to the customer's requirements. The corresponding AATCC method, 16.3, also has 3 test options to choose from. One of the questions we get asked regularly is how to select a standard or method that lies within a standard. We'll very quickly run through what each of the methods could be chosen for. I'd ask you to keep in mind that these are generalizations, and you would need more information on the product that you are testing to definitively select the appropriate method. So method 1, this method is considered the most informative and should be used in cases of dispute over the numerical rating. It's also especially suitable for the determination of colour fastness to light for test specimens of unknown performance. Method 2, this method is used when a large number of specimens have to be tested simultaneously. So this one allows a number of specimens differing in colour fastness to be tested against a single set of blue wool references, and thus conserving your supplies. There's method 3. This method is suitable where the test specimen is compared for conformity with a known performance specification. There's method 4. This is intended to check conformity with an agreed upon reference sample, and so the exposure period is controlled by inspection of the reference sample. This method is particularly suited as a quality control method and permits many test specimens to be compared with the same reference specimen. Method 5. This method is suitable to check conformity to predetermined radiant energy levels. So for methods 1 to 4, assessment of fading of the test specimens or reference samples is critical to obtaining valid results. It is not sufficient to rely on exposure time, in usually hours, to determine the end point of the various stages of each method. Method 5, the end point is determined by a specific dosage of irradiance, and intermediate assessment of fading may not be required. Now let's delve a little bit further into method 2, as this method is a great example of a test process with multiple steps to give you an idea of the complexity of light fastness testing. So here we are testing ISO 105B02, and this is method 2 using A1, which is a temperate zone with normal humidity. This method has 3 fades, and you would expect fade both on the blue wool reference card set and the specimens on separate mounting cards. The masks increase in coverage for each stage to effectively halt the fade on that part of the blue wool or specimen for later comparisons. We've mocked up a blue wool and made it a bit squarer so you can better see how the different wools will behave from fade to fade. So this test comprises of 4 stages on the blue wool, which you can see outlined in the yellow on screen. So a preliminary assessment is made when blue wool reference 2 reaches a grayscale 3 to check for what is called photochromism, which we'll talk about later in the presentation. On the first fade, you are looking for blue wool reference fabric number 4 to complete a shade change to grayscale 4, which would take approximately 40 hours. On the second fade, changing to the second mask on screen, you are looking for blue wool reference fabric number 6 to complete a shade change to grayscale 4, which would take approximately 160 hours. And then on the third and final fade, changing to the third mask that you can see on the screen, you're looking for the blue wool reference fabric number 7 to complete a shade change to the grayscale 4, which would take approximately 320 hours. So you have been putting your specimen through the same process, and this could be mounted in 2 different ways. So if you want to include multiple specimens or multiple parts of the same specimen, you can run them in rows as shown in our mock-up on the left-hand side of the screen. For one single specimen, you can use one large piece, which you can see on the far right-hand side. The final part of the test is the assessment of your specimen. You'll need to grade the specimen against the blue wool standard that has been created against each specimen's fade change. 3 grade results will be achieved. If it is the first test of a fabric with an unknown fade grade, it is better to proceed with caution and start by putting the test on for short assessment intervals. Try 1 hour at first and increase in small time intervals, as you don't want to overshoot the mark and fading of the specimens, because this can ruin the test and it can also waste many hours of testing that you've already put in. It is a little easier to judge the testing step time duration for tests like method 2, where blue wool are used as a guide, as you have an idea of how long the blue wools actually take to fade. However, caution should always be taken when setting the timings, and we advise creeping assessments up to these fade steps. So we've covered one method of one standard, and there are already many steps and a lot of detail. And this is the case for light fastness testing, which is in general quite a tricky topic to navigate. So our recommendation, as always, is to ensure that you read the standard, and for light fastness, multiple times, so that you're completely familiar with the steps that you need to take and what grading looks like once the test is actually completed. So, as you might be aware, our technical team run a support desk to help with testing issues, and we often see the following common issues cropping up with light fastness testing. A common misconception is that the blue wools are not a part of the assessment process. In fact, as you have seen from the testing examples we have run through, the blue wools are an integral part of the test. We see operators that are using the grayscales to grade and assess, which is ultimately leading to the results being misinterpreted and incorrect. Light fastness testing is generally a 2-step assessment consisting of assessing your blue wools to the grayscales while the test is in process, and assessing your specimens to the blue wools once the test is complete. Blue wools aren't used in every standard, which is why knowing your standard is so important here, but this rule should be applied for the majority of the standards that you use. Another common mistake users make is not using all of the specimen holders during a test. So for example, our True Fade at James Heal has 9 holders, and even if you're just testing one specimen, you should actually utilize all of the other 8 holders. The inside of the chamber is thermodynamic. So if you only have one sample, then this will absorb and reflect all of the light and heat, and the air will move differently too. And this can lead to exaggerated or inconsistent and ultimately inaccurate results. If you only need to test one specimen, there is no requirement to waste additional samples. You can put blank mounting cards in, and the black standard thermometer and black panel thermometer are used to take up one of the spaces. Sometimes a test doesn't actually run the way you would expect it to, or take the amount of time that it did previously. So if this does happen, you need to check to see if the exposure is set correctly for the test that you are performing. So what does this mean? Most test devices can operate in 2 exposure modes, and these are blue wool mode and irradiance mode. So blue wool mode, also known as nominal power mode, runs the xenon arc lamp at nominal 75% power, and the irradiance will not be controlled. Although many light fastness standards use blue wools as a means of grading the amount of fade, defining the level of irradiance is now becoming a lot more popular. This can be done in controlled irradiance mode, and it keeps the light output constant by measuring it and adjusting it as required. Tests can then be performed to a specific total irradiance, and by controlling this testing, times can be more predictable as the light is dosed constantly and at the same rate. As mentioned, this is a fundamentals webinar, so we won't spend too much time delving into the different modes. The important takeaways from this is check your settings before you run any testing and ensure that you are meeting the standard requirements. Another basic error we sometimes see being overlooked is preparing the test, and this is very easy to get right the first time. Mounting specimens correctly is important to ensure accurate and repeatable results. So some helpful tips we have for this: place the specimens on OBA-free white cards, that's optical brightening agent-free white cards. Attach using small non-ferrous staples. These small staples create less bulk, and non-ferrous staples won't rust. The minimum specimen size is 45 by 10 millimeters. Specimens should be free from creases or any folds. You need to ensure that the masks or the covers are clean and flat. And a reminder of a previous slide, place any white card in any of the sample holders within the machine. Something else to keep an eye on is all xenon arc lamps have a lifespan, and towards the end they will become less bright. Some instruments, like our True Fade at James Heal, will actually be set up to compensate for this by adjusting the power to increase the brightness, but there ultimately comes a point when the irradiance can no longer be maintained and the lamp must actually be changed. We know that this type of testing can take a long time, so we recommend checking the lifespan of the lamp before you start any testing and changing it if it's necessary to do so. When checking the lifespan of your lamp, you should be checking the odometer, which for our True Fade is built into the TestWise software, so you can see it on the control panel. This will notify you of how much time is left, usually in hours, with the lamp still in tolerance for testing. When a new lamp is replaced, the odometer needs to be updated so that the clock can start on the new lamp's life cycle. So we mentioned previously photochromism, and this is the light-induced reversible change of colour. So it's the temporary fading of a fabric. Standards have instructions to leave the samples in a conditioned atmosphere for a set amount of time after the test and before you have conducted your assessment. If you have graded immediately after testing, photochromism could lead to your assessment being completely inaccurate. There are separate and specific standards to test for this issue separately, but this is always something that you need to be aware of when testing your specimens for light fastness. So that's nearly everything that we have to cover today. So I'm just going to go into some key takeaways from this Fundamentals webinar. So when compared to other types of colour fastness testing, the effects of light can be far more subtle and unpredictable. So ultimately, we're trying to predict how the sun's rays will behave on your chosen textile. This type of testing can be complex, but can be conducted by most lab technicians so long as they are familiarising themselves with these standards and taking some note of our top tips as well, which is always really useful. The more tests you perform, the better you will understand your products and their strengths and weaknesses. You might also be able to streamline your test process if you work with the same fabrics time and again. So you can predict their behaviour and it can be much easier to do. It's also crucial not to bypass or miss out parts of the visual assessment, which includes the grayscale and the blue wool standards. The two-step assessment leads to an accurate grading for your product, so it should be followed whenever the standard dictates you to do so. Finally, a good light fastness tester should help with the test process. So preloaded standards are always helpful, having alarms for grading intervals, and having testers with general ease of use.
Thank you so much, Seth.
Thanks, Sharon.
If anybody has any questions, now would be the time to type it into the questions box, and we will deal with those. Just while people are thinking and typing their questions, I can let you know the topic of our next webinar. Next, we will be delivering a webinar called Fundamentals of Hydrostatic Head Testing. This webinar has been created in partnership with our technical specialists who have a wealth of knowledge and experience in performance testing. With their expertise, this webinar focuses on topics from what is hydrostatic head testing and why it is important, through to what potential issues might occur when performing the tests. This webinar will take place on Wednesday, 16th February and Thursday, 17th February at the usual time, and we will share registration links in a follow-up email. Hopefully you can join us for this important topic. I will give people another 5 minutes to type in their questions, but that is all the information we have to share with you today. Thank you for joining us.